Hello student, welcome to the course Analog and Digital Electronics, Unit 2 Design of Sequential Circuits. And in this Unit 2, during this module number 6, we studied the ring and twisted ring counters. This is the circuit diagram for the ring counters. As the name is the ring counters, the ring connections is there. Firstly, the 4-bit ring counters we have to utilize here. So that's why the 4 D flip-flops we use here. The ring connections is nothing but the output of the first flip-flops is connected to the input of second one. Output of the second flip-flops is connected to the input of the third flip-flops. Output of the third flip-flops is connected to the input of the fourth, and the output of the last flip-flops is again fed back to the first flip-flops. So in this way we are making a ring. So output of the first is nothing but the input of second, output of second is nothing but the input of third, output of this third is nothing but the input of fourth, but the output of this last flip-flop is connected, fed back to the first flip-flop's input. So this is the ring connection, and this connection is very important. Then the clock, synchronized clock, is applied to the all flip-flops, all the 4 flip-flops. The preset input is given to the first flip-flop only, and the reset input is applied to the all remaining 3 flip-flops. So for these connections, if we applied the preset input to the first and reset to the all other remaining flip-flops, the first state we are getting as 1 0 0 0. So this flip-flop 0 stored the 1 value. Why? Because the preset input is applied. So this Q0 flip-flops, FF0 flip-flops is forcefully stored a 1, and remaining all the 3 flip-flops is applied by the reset input. So that's why the remaining all the 3 flip-flops is forcefully stored the 0 0 and 0 data in that particular D type flip-flops. So for the first state we are getting here, so first flip-flop is the stored 1 and remaining all the flip-flops store the 0 value. Now for the next proceeding clock pulse, the output of this first flip-flop is shifting to the second flip-flops. The output of the second flip-flop is shifted to the third. Output of the third flip-flop is shifted to the fourth flip-flop, and output of the fourth flip-flop is shifted to the first flip-flop. Now see here, the output of the fourth flip-flop, the output is Q3 is the 0. Now this 0 is shifted, ringing back to the first flip-flops. So that's why the output value of this Q3 is shifted to the Q0 for the next clock pulse, and the value of this Q0 flip-flops is shifted to the Q1 flip-flops, because the output of this proceeding flip-flops is connected to the input of this next flip-flops. So that's why this value is ringing from 0 flip-flop to 1 flip-flops. And similarly for the next clock pulse, the value of or stored value of this first flip-flop is ringing again to the flip-flop 2. But here in this case, the value of this fourth flip-flop is again to be a 0. So that's why the 0 is again stored to the first flip-flops, and the output of this first is again connected to the input of second. So that's why the value of this first is shifted to the seconds, and we are getting the state is like that 0 0 1 0. For the next proceeding clock pulse, the value stored in the first flip-flops is shifted to the seconds, and similarly fashions it can be shifting to the third value, and the third flip-flop value stored value it can be shifted to the last flip-flops. Now we are getting the third, that is the fourth last flip-flops Q3. It can be stored the 1, and after the next clock pulse it can generate the value 1, and which is connected to the input of the first flip-flop. Means after this fourth state 0 0 0 1, we are getting the state as a 0 state 1 0 0 0. So first Q0 it becomes to be a 1, and remaining all the 3 flip-flops becomes to be a 0 for this state. So these are the 4 different states we are getting for the proceeding clock pulse, and this is the one of the drawback of this ring counter. We are only getting a 4 different output state for this 4-bit ring counters. So that's why in order to overcome that disadvantage, we are modified these ring counters and we call it as a twisted ring counters. So that twisted ring counter construction is like that, similar as the ring counter, but just a single changes we made here. The complement of the last flip-flop, complement means whatever the value stored in the last flip-flop, we are taking the complement of that output, and that complemented output is feedback to the first flip-flops. Now remaining all the ringing is the same. The output of this first is nothing but input of second one. Output of second is the input of third one. Output of third is the input of fourth or last flip-flop, but the complemented output of the last flip-flop is the input of the first flip-flops. And another change is that all the flip-flops initially we are resetting. Once we are resetting the all flip-flops, we remove the reset pin and continuously we are providing the synchronized clock pulse. So for each and every clock pulse we are getting or determine the different state output data. We have to see in it detail one by one. So firstly we are resetting the all flip-flops and remove the reset pin. So that's why for the first state we are getting all the flip-flop is in reset conditions, nothing but all the flip-flops store the 0 value. Now see, or concentrating on this last flip-flop, it can store the Q value as a 0, Q3 value as a 0, and we are getting, or we are taking the complemented output from this last flip-flop. So complement of this 0 is nothing but the 1, and this 1 is available as the input for the first flip-flops. So for the next proceeding clock pulse, so 1 is stored in the first flip-flops and remaining all the flip-flops stored the 0 value. Again it can be seen the last Q3 flip-flops stored value is the 0. So that's why it's generate the complemented output as a 1. This can be available at the input of the first flip-flop. So for the next proceeding clock pulse, so it can be again stored the 1 value, and the previous 1 value stored in the first flip-flops, it can be shifted to the second flip-flops for the next proceeding clock pulse, and similarly it can be shifted so on. For the next clock pulse, the stored value of this second flip-flops is shifted to the third one. The value of the stored value of this first flip-flops 1, which is shifted to the second flip-flops, and output generated by the last flip-flops, which is complemented output 1, is stored in the first flip-flops. Now here it can be shown up to this first 4 clocks, the output or store value of this Q3 is the 0, and we are taking the complement of that 0 as 1, and that's why this 1 is stored in the flip-flop 0, flip-flop 1 and flip-flop 2. But at this fourth or the fourth clock pulse, all the flip-flops is now becomes to be stored value as a 1. And keep in mind, the last flip-flop's stored value is the 1, so it output is generated as a 1, but we are taking a complement of that 1, so 0 is now present at the input of the first flip-flop. So for the next proceeding clock pulse, so 0 can be stored in the first flip-flops and remaining all the 3 flip-flops stored the 1 value. And for the next proceeding clock pulse, so the 0 can be shifted to the second, but the last flip flop is continuously generating a complemented 0 output, which is nothing but a 1. Okay, so in this way, in the similar fashions, we are getting 0 0 ringing continuously up to the 7th or 8th clock pulse. 8 clock pulse we are getting the similar data as a 0 clock pulse. Okay, so initially data and final data we are getting the same. So this is the state diagram for this Johnson counters, and in this way the data can be continuously ringing. Firstly, the 0 data is ringing for the 4 clock pulse, and the remaining 4 clock pulse the 1 data is ringing. So you clearly seen that the 1 1 1 1 1 1, and then it can be 0 0 0 can be stored, and in similar fashion the 1 1 1 1 data can be ringing for the 4 clock pulse, and then 0 0 0 0 data can be ringing for the 4 clock pulse. So in this way, for the same physical requirement, nothing but in case of ring counter we are using a 4 bit, and instead we are getting the output as a 4 state output. Similar in case of the two-state ring counter, we are again utilize the same physical model 4 bit data, but even though we are getting 8 different distinct output state. So that is the only the advantages of this twisted ring counters, and we are utilizing it for the different applications, or because it's we are getting as a 8 different output state. So thanks for watching this video. If you have any queries, so ask me anytime on my personal gmail.com, my official gmail.com, that is the chandrakant.shinde@education.in, or my WhatsApp 9970031353. So thank you for watching this.